Hi everybody, welcome to section 3.3. Very simple. We're going to cover two basic rules of probability, so shouldn't be too difficult, and we're going to do some super fun examples, of course. So let's get into it. The first one is called the multiplication rule. So by now we know if we have two events defined on a sample space, then the probability of the events, the intersection of the events or them occurring at the same time is equal to the probability of one of them. So probability of, let's suppose, B times the conditional probability of A given B. All right, so then it goes the other way as well. So if you have the probability of A times the probability of B given A, that's equivalent to the intersection as well. And then if I was to take this and solve for the conditional, you have this familiar formula from last time. Now, if they're independent, that means that the conditional probability is equal to the numerator's probability of B, right? I mean, the actual probability. And then the intersection will just be the product of these two. Because see here, I'm substituting probability of event B for the conditional probability of B given A. Okay, so you might think like, well, that was what you need to know. And let me tell you, all you really need to remember is you need to remember this guy. If they're independent, okay, if they're independent, this is true. But in general, this is true. Okay, this is whether they're independent or not. Okay, now the addition rule. Suppose you have two events defined on a sample space. Now the union is equal to the event of one plus the probability of the other event occurring minus the probability of the intersection. Okay, so let me just this is going to be a terrible drawing, but we're going to try this. Okay, so remember in the beginning where we had, here's our sample space, here's A and here's B. Okay, if you have the probability of A, that's this right here, right? A. What's going to happen? So let's say I'm using all this area. Okay, remember that area represents a probability. Sorry, I went too far. I'm going to erase this because that's not, oh no, I erased everything. Okay, let me try this again. So here we have everything. We have here, the sample space. And let's say this is event A and this is event B. Okay, and the probability of A is like this. Okay, this is the probability of event A. So let's say this is B. Okay, I got another color. This is terrible. I'm going to figure this out. Okay, so when I do both of them, okay, if I want to talk about the union, I want to find out what all of it is, right? But notice, okay, so here's probability of A, the red, probability of B is the blue, but now look what we're double counting. What are we double counting? If you said the intersection, you're correct. So we need to subtract the probability of the intersection occurring because it's being double counted. Now, consider this. If they are mutually exclusive, what does mutually exclusive mean? That the probability of both of them is equal to 0. So if I was to draw a very crude, terrible sample space here, what's going to happen is you have A here. Remember, there's no intersection. So then B would be over here, right? Okay, so then if I want to take the probability of the union, I'm just going to do probability of A, sorry, it's filled in, and then plus probability of B, okay? I'm sorry, it's terrible, but I hope you guys understand what I'm trying to do. Looks like a 5-year-old drew on this, but that's all right. Okay, so let's do a super fun example. Let's say Juan is trying to choose where he wants to go on vacation. Let's say he has two choices. A is New Zealand and B is Alaska. Juan can only afford one vacation. The probability that he chooses A is 0.6, and the probability that he chooses B is 0.35, okay? So note that he can only afford one vacation, so the probability of both happening is 0, okay? He can only afford one. Okay, so what's the probability of A or B, the union, right? is probability of A, which is 0.6, plus the probability of choosing B, which is 0.35, minus the intersection, so that's 0.95. But that's not exactly 1. What's left over? The probability that he doesn't go on vacation at all must be 1 minus 0.95, which is 5%. All right, let's do another example. Let's say a student goes to the library and the events are B, student checks out a book, and D, the student checks out a DVD. What are those? Those are the round things that movies come in. Okay, suppose that the probability of B occurring is 40% or 0.4 in decimals. The probability of the student checking out a DVD is 30% or 0.3. And the conditional probability of D given B is 0.5. So let's say we wanted to find the probability of the intersection, and we wanted to find the probability of the union, so and or. And this is an and right here. Remember, and is the upside down one, and or is the union, the U. Okay, so probability of B and D is equal to probability of B times the conditional probability of D given B. Well, that's good because we have this, we have P of B, and we have P of D given B. So we just take the product, and that's it. Now, if we do an or, right, the or is the one where we have to add and then take away the intersection. So we just add P of B plus P of D minus the intersection with this, which is what we just calculated. So 0.4 plus 0.3 minus 0.2, and that will give us 50%. All right, and I believe this will be the final example. Studies show that 1 woman in 7, approximately 13.3%, who live to be 90, will develop breast cancer. Suppose that of those women who develop breast cancer, a test is negative 2% of the time. Okay? Also suppose that in the general population of women, the test of breast cancer is negative about 85% of the time. So let B represent the woman who develops breast cancer, and let N represent the event that the tests are negative. And suppose one woman is selected at random. What is the probability that this woman develops breast cancer, and what is the probability that the woman tests negative? Okay, so let's think about that. Okay, so A, the probability that the woman develops breast cancer, it's right here. 14.3%, it's already given to us. P of B is 14.3. Okay, and then let's see here. What's the probability that the woman tests negative? Okay, so here in the general population of women, the test for breast cancer is negative about 85% of the time. Okay, so that's 0.85. Okay, fine. Now it says here, what's it called? Given that the woman has breast cancer, what is the probability that she tests negative, right? So see if you can figure out how you would write that symbolically, and then what's the numerical value. So given that the woman has breast cancer, so right away, that's after the given, what's the probability that she tests negative? So they're asking, what is the probability that a woman tests negative for breast cancer given that she does have it? And that's N. If you said P of N choose B, or N given B, I mean, that's correct. And here it is, this sentence right here. Suppose of those women who develop breast cancer, test is negative 2% of the time. Okay? And then C, what is the probability that the woman has breast cancer and tests negative, right? So remember, it's an and, P of B and N, right? So then that's our multiplication rule right there, right? P of B and N is P of B times P of N given B. So we have all that information. We have 0.143 times 0.02. So that's our probability of both of them occurring. Okay, let's continue. Same problem. What's the probability that the woman has breast cancer or tests negative? So this is a union now, so we need to do the addition rule, okay? So remember addition rule? P of B or N is P of B plus P of N minus the intersection, right? So that's just from earlier, 0.143 plus 0.85 right here minus what we just calculated, 0.0029. So that's the probability of the union of the two events. Now, are they, is having breast cancer and testing negative, so are those considered independent events? Okay, so how would we know that? We would know that because what? Remember that P of N is 85.85%, and P of N given B is 0.02. Remember, for them to be negative, they have to equal. P of N has to equal P of N given B, and they do not, so they are not negative events. Are they mutually exclusive? Do you remember what's the criteria for being mutually exclusive? The probability of the intersection has to be what? If you said 0, good job. And is that 0? Is the probability of B and N 0? No, it's not. Remember, we calculated it earlier, and it was 0.0029 or 0.29%. And since it's not 0, that means that the events are not mutually exclusive. Okay, and that's it for 3.3. And that's your homework. Good luck. Make sure you watch the other videos, and I will see you on the next one.